So, welcome everybody to the last part on non-coherent modulation techniques. In today's lecture, we will discuss differential phase shift keying. And if you remember with me in the last part of the lecture, we said that phase shift keying, you can only demodulate it coherently because it depends on the phase. And phase is very critical for the carrier. You must be able to generate the same phase. But what if we want to send our data and receive our data non-coherently using phase shift keying? Then we must use something called differential phase shift keying. Then what's this differential phase shift keying? How do we implement it? What's its performance? How does it compare with the other non-coherent schemes like frequency shift keying or the other ones? Is it good to use it? How to get the maximum out of it? So in this lecture we will understand and be able to answer all these questions. So differential phase shift keying is the non-coherent version of frequency phase shift keying. Phase shift keying is the coherent, differential non-coherent. It eliminates the need for a coherent reference signal. You don't need reference phase or anything. To do that, you do two things. First, you encode your input binary stream differentially. You encode them differentially. And then you apply phase shift keying modulation to the encoded binary data. You map the bits to different symbols. Differential phase shift keying, instead of finding the phase of the signal on the interval from 0 to TB, this receiver determines the phase difference between adjacent time intervals. So, the receiver task is not to determine the phase of each symbol at a time, but you measure the phase of two consecutive symbols and you find the difference between them. Based on this difference, you decide whether one was transmitted or zero. If one is sent, if one bit was transmitted, then the phase of your signal remains unchanged. If zero is sent, the phase changed by 180 degrees. Suppose that the transmitted differential phase shift keying is signal equals to the following formula, which is square root of EB over 2TB cosine 2 pi FCT for the period from 0 to TB, where TB is the bit duration, EB is the signal energy per bit as usual. Let S1 of T denote the transmitted differential phase shift keying signal for the period of 2TB for the case when symbol 1 is being transmitted for the second part of this time interval from TB to 2TB. The transmission of symbol 1 leaves the carrier unchanged over the duration of... So what this is simply saying that if you transmit 1, the carrier phase does not change in your carrier for 2TB. If you transmit 0, it changes. So it's certain phase in the first duration TB and changes to another phase. The transmission of symbol 1 leaves the carrier unchanged over the interval of 2TB. Therefore, we can define it as follows. S1 of T, when you transmit 1, then the signal over the first period is this, and over the second period is this. This means it's the same, no phase change, nothing changes. While when you transmit S2 of T, which corresponds to 0, then the signal in the first bit duration is similar to this carrier with 0 phase, while in the second duration bit is carrier with pi phase. So this means there is a change here. So if there is a change, this means that you transmitted 0. If there is no change, you transmitted 1. The average probability of error if differential phase shift keying signal can be given as follows: half exponential of minus EB over N naught. A comparison between the average probability of error of differential phase shift keying. If you compare the bit error rate of differential phase shift keying with the non-coherent binary phase frequency shift keying, you will see and notice that differential phase shift keying has better bit error rate than frequency shift keying. So if your application requires high reliability with low complexity, which modulation you use from the following? Differential phase shift keying, frequency shift keying, non-coherent frequency shift keying. Which one? This is a question in the exam. If your application requires high reliability, which means low bit error rate, and low complexity, which means non-coherent, which of the following modulations you use? The answer is not here. The question is not here in the slide. Just from your understanding, you need to answer it. So what do you think, guys? Differential phase shift keying. Why differential phase shift keying? Because I'm saying low complexity. Frequency shift keying and phase shift keying doesn't give low complexity because there is coherent. You need to regenerate the phase of the carrier. And low reliability. Then differential phase shift keying because its bit error rate is lower than non-coherent frequency shift keying. Got it? Similar to these questions I will ask maybe in the multiple choice. Generation, how to generate the differential phase shift keying. Let the binary sequence PK, this is the binary data sequence, represents the binary data to be transmitted using differential phase shift keying. And let the sequence DK represents the differentially encoded sequence. Then you can follow the following rule. If the incoming binary symbol PK is 1, leave the symbol DK unchanged with respect to the previous bit. If it is 1, don't change the current bit with the previous one. If 0 comes, then change the current bit with respect to the previous one. The differentially encoded sequence DK, which is the resulting, do you know why do we call it differentially? Because always you look at the previous one and see if there is change, if 0 comes, you change with respect to the previous one. So there is kind of differential relationship between them. The differentially encoded sequence DK is used to phase shift a carrier with phase angles 0 and pi representing symbols 1 and 0. Now you got your differentially encoded sequence. How do you map this to phases? If it is 0, keep the phase of your carrier 0. If it is 1, keep the phase of your carrier, make the phase of your carrier pi. 0, 0, 1 pi. Now, this is the important example. Give you sequence BK and tell you, consider the binary sequence shown below. Find the differentially encoded sequence and the transmitted phase of the carrier for differential phase shift keying modulation scheme. You tell me, okay, BK, these are the bits you want me to transmit them. Yes, I want you to transmit them. You tell me I need to find DK. Forget about DK minus 1 this. The second column, forget the second row, forget about it. I'm here. I need now to find DK. And I give you this one. You need to fill this and this, for example. If 1 comes, and you have what the rule of differential modulation says, if 1 comes, then don't change the current bit with the previous one. What was the previous one? 1. This is reference. So this must be 1 because 1 comes, I don't change with respect to the previous one. Now 0 comes. When 0 comes, then change this bit and make it different than the previous adjacent one. So if it was 1, make it 0. If it was 0, make it 1. Now another 0 comes. What's this? 0. This must be 1. 1 comes, and this one, keep it unchanged. And you continue like this. So you got it? I give you this sequence. I can give you any sequence, not necessarily this sequence. I give you this sequence and give you this reference signal and find the differentially encoded bit sequence. You say if 1 comes, I don't change this value with respect to the previous one. If 0 comes, I change this value with respect to this. So if this 1, this becomes 0. If this 0, this becomes 1. Now, what's the phase of the transmitted signal? You tell me if it is 1, I map it to 0. If it is 0, I map it to y, according to your mapping rule. Clear? This is how you build your differentially encoded sequence and differentially encoded signal. How to generate this? Differential phase shift keying modulator can be realized by the block diagram shown below. You have the input binary BK, logic network here. You have DK, you take this DK and delay it by TB, you have DK minus 1, and you let BK and DK minus 1 enter to the logic circuit and to get the final value of DK. And then you have amplitude level shifters, after that product modulator, and then your differential phase shift keying signal is ready to go through the channel. The receiver, what do you do in the receiver? You get your signal, you get the in phase, the quadrature, you multiply by cosine this, and then integrate. This is correlator, and here you delay and multiply by the direct path so that you get the differential value, and you do the same. This is correlator, dot product operation, and you delay your path with respect to the direct path, multiply them with each other, and then sum, and you take y. Then you have decision device that you can use it to compare. If y is greater than 0, then what you transmitted is 1. If y is less than 0, then what you transmitted was 0. The threshold here is 0. And this is the rule that I used to decide on this, the mathematical rule. From the block diagram, we have that decision. If xi0 multiplied by xi1 plus xq0 multiplied by xq1 greater than 0, then 1 was transmitted. If it is less than 0, then 0 was transmitted. If the phase of signal is unchanged, send 1. If it is changed, send 0. This is the thing you need to consider. Here changed actually, not unchanged. If it is changed, send 1. Signal space diagram of received differential phase shift keying signal. This is the in phase of the signal. This is the quadrature. These are the message points. This is the basis function along in phase, basis function along quadrature, and you use this to see where is the position of your symbols in the constellation diagram. Now we want to make a comparison between the bit error rate performance of different modulation schemes that we have studied so far. We have studied coherent binary phase shift keying, coherent quadrature phase shift keying, coherent minimum shift keying. The bit error rate of all these three is half ERFC square root of EB over N naught. So QPSK, binary phase shift keying, and minimum shift keying, they have the same bit error rate. Now, coherent binary phase shift keying has this formula, which is 3 dB less than this. Differential phase shift keying has this formula, half exponential 2 minus EB over N naught, and non-coherent binary phase shift keying has this formula. So as you can see, these are the best three. After that, this comes. After that, this, then this. Now let's draw them. These are the formulas. Let's simulate them and see the bit error rate performance using MATLAB. These are the best three ones. Coherent binary phase shift keying, QPSK and minimum shift keying. They have the same bit error rate. Bit error rate represents the error versus the signal to noise ratio, EB over N naught. Then now, what the second best one? Which one? This curve, yes, because it's closer to this y-axis. What's this? Differential phase shift keying. The third best curve is this. What's this? Coherent binary phase shift keying. And last one, which is the worst bit error rate, is non-coherent binary phase shift keying. So, if I come and tell you, I have an application, I put also other curves. I put 16 QAM, 64 QAM, and tell you if I want, if my application requires high throughput, which modulation you use. I don't care about bit error rate. Among these, which one you select? I will give you a figure and ask 10 questions, maybe multiple choice about it. Figure like this. If the application is requiring high throughput, like augmented reality application, gaming, online gaming, virtual reality, augmented reality, mixed reality, online streaming, you need speed internet, high data rate. Which modulation scheme you say? You will choose. I will put in the options DBPSK, QPSK, differential phase shift keying, differential minimum shift keying. Which one? I'm not saying anything about reliability. I'm saying just I want high throughput. You just look at the curve that gives you maximum throughput. Which one gives you maximum spectral efficiency? QPSK. Why? Because QPSK sends 2 bits per symbol. The correct answer is QPSK. Now, I tell you an application that requires best bit error rate, low errors, high reliability. I put in the first option phase shift keying, then QPSK, then coherent minimum shift keying, and then the fourth option, all of the above. Which one you select? Which one you select? All of the above, because all of them, they are good. Here, they are the same in the figure. They are exactly the same. I'm not asking you to memorize the figure. The figure, this, I will give it to you. Yeah, put it in front of your... Either I give you the figure or I give you information and draw the figure. But one of them will be given to you. So this is not memorization, understanding. Understanding what each modulation gives you in terms of bit error rate and the throughput, spectral efficiency, the features of each modulation, the characteristics, and how to map them to applications. An application that requires low complexity, extreme low complexity. What do you choose? You choose something non-coherent. So if I'm giving non-coherent and coherent, always choose the non-coherent. Something like this, the question. I may ask you sort the following modulation order according to their spectral efficiency, according to their bit error rate. You must be able to do these things. What's the difference between QPSK and offset QPSK, for example? What are the differences? Why do you use this? Why do you use that? So these kind of questions, you might see them in the test. And this is just to make sure that you are understanding things in a clear way and things are making sense to you and you have intuition to decide which modulation for which application. So with this, we conclude our lecture about binary non-coherent differential phase shift keying, and we continue next week with your presentations where you present and I give you feedback and comments about your work. Thank you very much and meet you next time.